Hi, my name is Joshua Villegas. I'll be recording the first half of this Project 2 Fluent tutorial. So we're going to start by dragging this Fluent project into the workbench. We're going to design our geometry using Design Modeler. Before we do anything, we should change our units to millimeters since we're working with a 30 centimeter flat plate. But for fidelity and just ease of working, I'm using millimeters so that we can apply the thickness of 0.1 centimeters, or in other words, 1 millimeter. So we're going to go normal to our XY plane. We're going to create a sketch on our XY plane. And because we want to get results over our flat plate, we want the origin to be the top left of our flat plate. So we're going to create a rectangle starting at the origin, like that. We're going to dimension it. It's going to be 300 millimeters or 30 centimeters by 0.1 centimeter or 1 millimeter. So now we have a really thin flat plate, and we want to draw another rectangle for our control volume. Just a really big one. And I like to make my control volume symmetric around my flat plate. So to do that, I'm just going to draw a vertical line and a horizontal line along the x-axis. And I want to make sure that this line is halfway through the flat plate. So dimension it to be 150 millimeters from the origin, like so, and then constrain the sides of our rectangle so they are symmetric, like so. And now go the dimensions for our control volume. I used 900, actually 1,000 by 1,000. Oops. So that is our control volume, and then we can get rid of these lines. Then we are finished with our sketching, and we want to create a surface from the sketch. Oh, but let me make sure I'm highlighting from this sketch. And generate. So now we can see that we have a flat plate here. So we're done with that. Exit out. Now we're going to move on to our mesh. Take a little bit. Nice. So let's go view this normal to our XY plane. To start our mesh off, we want to start with a method and select this body. We want to use the triangle dominant. Then we're going to insert an inflation method. Got this entire medium, and the boundary we want is going to be the top and bottom. And personally, I used first layer thickness, so I can define first layer height to be really small since we want very accurate visuals on our boundary layer. I use this because we're working with a really small thickness. And then maximum layers between 70 and 90, so I chose 80, growth rate of 1.01. Generate. Now you can see we have very fine detailed cells close to our plate, but we also want to have a lot of divisions along our flat plate and not just these 4. So to do that, we're going to insert sizing method at the top and bottom edge. I'm going to switch to the number of divisions. I believe it did around 500. And we're not going to capture anything. And behavior is going to be hard with no bias. So now we can see that we've made a lot of divisions along the flat plate. So give us very accurate results as we travel down to the trailing edge. And then we want to also add another sizing for the left and right edges. We're going to use a number of divisions with, I think I used around 20, and left everything else. Because we want to make sure to capture the impact of the airflow at the edge. So now that we have that, we have a very fine mesh towards our plate, but we also want to make it fine around our plate. And so I just changed the element size to 0.15 to -2. Anything smaller than this kind of broke my computer, so I'm going to keep it around that. This might take a minute. So now that this is finished, we can see that we have a solid mesh required to analyze our boundary layer close to our flat plate. So the last thing that we have left to do in this section is to name our edges. So for this, it's going to be our velocity inlets. This is going to be pressure outlets. The top and bottom edges are going to be our symmetry. This is the front wall. Upper wall. So if we go to our name selections, we can see all of these. Nice. So we can exit out of this, right click, update. Nice. So we go into our setup. I use double precision with 4 solver processes. Nice. So we are analyzing the boundary layer. So we're going to have for the viscous model, we're going to choose laminar and make sure that our fluid properties follow that of the assignment, which we had 0.2 for the density and 1.8 E-5. Close that. And now we want to make sure that, yeah, we're using air. Now we go to our boundary conditions. So for the velocity inlet, we're working with 15 meters per second. And everything else should be the same. Next, reference values, compute from the velocity inlets. And then for the initialization, I use hybrid with 25 iterations. And then for calculations, I use 200. Oops, forgot to initialize. And then we can start a calculation. So our calculation is complete. And for this project, we, aside from analyzing the boundary layer along the flat plate, we also want to be able to look at the skin friction coefficient and the wall shear stress. So to do that,